One of the more important concepts in physics is momentum, which is what we will be talking about in this mini lecture. And you may notice that this equation right here is probably different than the equation you've seen before in your high school physics class if you had one. The equation that your high school physics teacher gave you was just an approximation. That approximation is only valid at what we would call lower speeds. This equation right here is referred to as the relativistic momentum. Relativistic means related to Einstein's theory of relativity, which deals with objects moving at speeds very, very faster than what we're used to, typically speeds that are approaching the speed of light. So the equation here is P equals gamma mv. Gamma is the relativistic correction factor, and it's a little hard to see in this script, but gamma usually drawn something like that. So right here we have the definition of gamma, and it's 1 over the square root of 1 minus the quantity v over c squared. So notice this is a magnitude, this is speed. All right, we're taking the magnitude of the velocity vector. C then is the speed of light, which is about 3 times 10 to the 8 meters per second. So, a couple things I want to point out. First off, P equals gamma mv. This right here, gamma m, is a scalar quantity. V is a vector, and P is also a vector. It's important that you start to identify whether these things are scalars or vectors, because vectors, remember, have a which way component to them. Vectors also tell you which direction something is acting. Now, we can rewrite this vector v in terms of its magnitude, which we sometimes call the speed, and then the unit vector, which is v hat. That gives us the direction. So if I go ahead and plug this in here, we get that P is equal to gamma m, the magnitude of v times v hat. So this right here is a scalar quantity. This is a unit vector. And what I really want you to notice here is that gamma and m don't affect the direction. The unit vector doesn't change. Gamma and m only change the magnitude. And this is true whenever we multiply by a scalar. If you multiply a vector by a scalar, you don't change the unit vector, you only change the magnitude of the quantity that you're dealing with. So let's just take a look at some values of gamma and see how big a factor they really are. So right here, this is actually figure 137 from your textbook, but in this column we have a bunch of velocities measured in terms of meters per second, all the way from 0 up to the speed of light. This is that ratio of v over c that you see in the denominator of gamma. And then right here, this is gamma itself. So notice that for 0 meters per second, 300, gamma is 1. Even when we get up to 3 times 10 to the 6th meters per second, that's pretty fast. We see that gamma is only slightly different than 1. We get up to 3 times 10 to the 7. That's about 10% of the speed of light. You can see that the effect is 1.005. So it's all the way here in this decimal place that we start to see any sort of impact. It's only once we get up to even larger fractions of the speed of light. So here we're at half the speed of light. Gamma's still 1, a little bit larger than 1, 1.1 something. Once we get up to, say, 99% of the speed of light, then we start seeing that gamma gets to be larger and larger and larger. And if we try to set the velocity equal to the speed of light, we see that gamma becomes infinite. That's an impossibility. That's something that just can't happen. So that's one of the reasons that we don't see objects being able to move at the speed of light, except for light itself. Now, one thing that I want you to answer for yourself before you're done with this section is, for values of v much, much less than 3 times 10 to the 8th, much, much less than the speed of light, what value does gamma have approximately? So if you had to make a rough approximation on the back of an envelope, what value could you write down for gamma, assuming that v is much, much less than the speed of light? And in that case, what's the approximate momentum equation? What is the approximate momentum equation when v is much, much less than c, the speed of light? Now, we'll be working some problems in class, and I expect you'll be working some problems on your own. So hopefully you'll start to gain a better idea of what momentum is. But what I want you to ask yourself is, how would you describe this to a friend who doesn't have a physics background, doesn't really understand math? How would you explain the concept of momentum to them without using equations? One thing you're going to find in this course is that some of the terms we use have fairly broad colloquial meanings. Everyday meanings for momentum are fairly common. But in physics, we have a very, very strict, very specific definition, and it's important that you understand that. So it's a good idea to spend some time in each section figuring out what do these terms mean, how would you go about describing it. It might be a good thing to write down in your notes or something, or try practicing on a friend. How would you describe these things? If you can describe them to somebody, chances are you've got a reasonably good understanding of how these things work.